Yes, I do have class. Why do you ask? I do. Why do you ask?
Oh, I had something to share. I don't remember what it was now.
Well, very happy to see you. Thanks for not forgetting that from time to time we meet here. And what are we going to do? Mostly chatting. I was trying to do some derivation for today, but I failed while preparing. So I'm not sure that it would be a good idea to reproduce. Or we can try to do it and find the error. How many meetings do we have?
3.
3 meetings or 3 weeks?
3 meetings.
3 meetings?
Next
This
week is the last week.
Then we have next week, which is dead week, and then finals week, which we don't have
No,
class.
next week isn't a week.
But it was.
Next week is a dead
Next week is a week.
No, it's a dead week.
Next week is the week.
Yeah, it's a week, but dead week. Yeah, it is.
I'm
But
looking at
how-
it right now. I know finals week is the
I think next week's a week, then we have dead week, then
no.
finals.
So today is the 25th, and then next Monday is the 1st. So that's the first week of dead week, and then we have the 8th, which is the first week of the finals, and then the 12th is the last day of the semester.
Oh, very complicated. So, how many
We
meetings?
have this week, which
Two
is
meetings. 2 meetings.
2 meetings.
yes, and then we have next week, which is dead week, and
Which,
then
which means what?
that's the last week of classes.
Okay, so 4 meetings.
Yes.
And then if we like, we can do presentations or exams later, or we can finish. But only 4 meetings for like lectures.
Yes, and then we're done.
So we have class on dead week?
Yeah.
Then why do they call it dead week?
Because dead week is a week that you study finals. Okay.
We are going to dead week.
Something about homework, no assignments.
Yeah,
or
you
something.
no, it's tests
Yeah,
and
in
quizzes.
dead week
You
you
can't
can-
have anything that's.
Let's forbid quizzes and homeworks for anything.
Okay.
So last time we did some not numerical, black and board theoretical illustrations to the concept of classical bath, noisy bath. I'm trying to remember who we are and what we are doing, and it looks like we are trying to work on non-equilibrium phenomena, and we are trying to depart from isolated quantum system. We are going to look through the methodologies that allow to treat quantum relaxation, or relaxation in general, so that whatever system, quantum system relaxes through some sort of friction and comes back to the ground state. Before that, we developed our, I wouldn't say mathematical muscles, but skills by looking through Bloch equation for quantum system under strong field, non-perturbative limit field. And then we started to look how the rest of the world affects the quantum system. And we looked through mechanism related to inhomogeneous broadening. If there are several replicas of the system for little different frequencies, which allows for free induction decay and echo effects. So this was a key to one of the 2 relaxational phenomena, the dephasing, transversal dephasing, transversal relaxation. And next, we posed the question, what does happen to populations? How to relax the population from excited state to the ground state? and we came up to the conclusion that just homogeneous broadening is not sufficient. One needs some randomness in the environment. When we met last time, we derived, or we did attempt to derive the equation of motion for electronic degrees of freedom in the Liouvillean formalism, like density matrix and this Liouvillean operator, upon implementing second order perturbation from the noisy bath. So the bath, like external field, has random phase, random amplitude, and then we are getting transitions between populations. Occupations at different levels exchange. This was our big victory, which is partially good, because it was working well only for what? For which temperature? 0 or infinite? No.
Infinite.
Yeah. So we neglected quantum nature of the surroundings around our quantum system. We assume just that it is random noise of a classical nature. So there are no quanta, there's just something that shakes randomly. And then as a result, we got that population is changing, but it is changing in equal measure with excitations and de-excitations in average, so that if the system has only 2 levels, they will come to 50-50 population, which will correspond to infinite temperature. If we want to be more practical, by the way, the handout that I distributed is illustration from textbooks about this noisy classical bath environment. But if we pose a goal, if you want to describe detailed balance, if you want to see that we have preference for relaxation over thermal excitation, then one needs to take into account quantum nature of the bath. So we will chat a little about differences between classical and quantum bath and how do they affect the equation of motion for electronic degrees of freedom. Make sense? So, another handout is on quantum bath, and I will be trying to follow this handout through a couple of meetings. So if you don't trust me, you can trust the book, because it has the author and title and year of publication. So it's our meeting number 23. Administratively, I don't know, just if you have steam and time, come tomorrow at 6 for some entertaining lab. I think it will be number 9. The table for comparing classical versus quantum as a motivation, and then we need to cover several things. If we introduce quantum bath, we need to discuss its Hamiltonian, but I will try to skip it and postpone for the next meeting. Then we'll try to justify that one of the simplest models that we know from the past, harmonic oscillators, are very good tool as a model for quantum path of any nature. So there is, one can use models of collection of oscillators for very broad distribution of very broad natures of the path. And we may recall the notation. What else do we need? The role of correlate function. Then we need to chat about Boltzmann, Bose-Einstein partition function, and average number of points. So, although our goal is to describe, to relax, not for us but for system, describe relaxation, we will not achieve the goal today. If we try to do it, it will be too scrambled, too jammed, and we will not be able to see the logic in a reasonable way. We better split on smaller pieces, prepare components, and then mix them together maybe next time. So do not expect shiny result today. I wouldn't say it will be extremely boring. It will be just chatting, maybe scratching something. It will be neither shiny results nor mathematically boring. To relax is a goal. We can assume that the relaxation appears due to presence of environment. Right. So when you do thermodynamics, which concept do you use?
Heat
Huh?
bath, heat bath.
Heat. Yes, heat bath, thermal equilibrium.
You could also use constant energy.
Yes, but we are not going to do it. We are going to use constant temperature. Hot plate. What's this sophisticated word for hot plate? Thermostat. So the idea is that if we put an object into the bath, the temperature of the bath will not change. So although there is an exchange of energy between object and the bath, the object may heat up or cool down, but the bath is not, because it is so big. It doesn't feel these little changes. And this is the main idea. But now, instead of this little duck, we will use whatever quantum system. And instead of bath, we will use either noisy environment or collection of quantum systems in thermal state. So we can reach our goals by either classical noisy bath or by quantum bath. And before we go forward with derivations, we can start right away with the analysis. So we do have two types of relaxational phenomena. Which ones? The transversal dephasing, which correlates, refers to free induction decay, right? You agree? And another one is depopulation, change of the occupation of the layers. Depopulation. And we can analyze how good our approaches are for dephasing at we can try at 0 temperature, room temperature, and infinite temperature. But let's skip 0 temperature, talk only about room, like ambient. Finite temperature and infinite temperature. Finite temperature and infinite temperature. So for dephasing, the larger temperature, larger the amplitude of this noise. So we are fine with finite temperature dephasing. And for depopulation, when we used noisy bath, it was working only in the limit of infinite temperature. When excitation and relaxation due to interaction with the bath occur with the same rate. Excitation rate. Excitation equal to the rate of relaxation. But for finite temperature, our noisy bath doesn't work. Probably it is okay here. But major problem that classical noisy bath doesn't allow us to pursue detailed balance from the rigorous first principles. A lot of researchers find a compromise. For atomistic modeling, one uses noisy bath due to like random motion of nucleus. One finds couplings, but then detailed balance is contributed by hand as an approximation, as an external procedure. If one wants to derive everything from first principles, then this approach doesn't allow it. It allows only infinite temperature. So this is the reason why we need to look at the quantum bath, so that it will allow to describe disproportion of two flows of energy that come in and out. So we hope that everything will be perfect here. But we do not know. We just want to explore. And we can formulate our goal, our purpose, that we want inequality. We want a disproportion between flows of energy in and out. I have done the major part. The rest are details. Are there any questions? No?
So that's what you mean by detailed balance, being able to account for differences.
Yes.
Right.
Yes. So, done with table, done with volume. So when we meet another time, we will talk more on the Hamiltonian, because those of you who attended recent Senegal Symposium and heard the banquet talk by Kieran Book, you've heard how one can trick colleagues and spend all the time just discussing the Hamiltonian. So we are not going to discuss it today. But if we introduce that the bust has some specific nature, we need to introduce Hamiltonian of the system of a bust in their interaction. And we will need to impose some restrictions. But here is the statement that I invite you to believe for 2 days, and then we will try to improve or provide more arguments. So that whatever physical nature of bath is, there is a way to formulate it as a collection of harmonic oscillators in the thermal state. So for any Hamiltonian, for most can be represented as a collection of harmonic oscillators in equilibrium, thermal equilibrium. Right? So Hamiltonian for one oscillator, then so many oscillators with different frequencies and their just index summation. I'm making anything possible to avoid literal discussion of the Hamiltonian. I want to stay general for a long time. But typically, the interaction is formulated in bilinear form, whereas the product of operator that affects our quantum system and operator that affects the path. How can we accept it? How can we rationalize this statement? Well, by now, the only source of this belief is Judd. He presented, he made a presentation on so-called James Cummings model, and he wasn't proving it, but he tried to convince us that mode of electromagnetic field in a resonator can be considered as a harmonic oscillator. Right? So if it is an electromagnetic field close to ground state oscillations, it can be considered as oscillators. If it is nuclear motion, they also, at low temperatures, they perform oscillatory motion. So at least this is not approved by any mean, but it shouldn't sound as a too wild of idea. Now we need to bring in another harmonic oscillators are used. We'll talk more about commutators, but let's recall what Aaron was presenting. What was his talk about? I know that Aaron knows himself, hopefully.
Autocorrelation.
Huh?
Autocorrelation function.
Yes. And actually, we did the same in class last time, at a little simpler, and more restricted extent than error. But we agreed. So most of the things that we are doing can be done rigorously by proving step by step. We just try to save time and make our life easier, and therefore it is more like a narration story. But we were demonstrating, we started to believe that the rates of the relaxation can be obtained from second order perturbative contribution to the equation of motion to electronic degrees of freedom. And if one unwraps this statement, then one does see that the rates are proportional to autocorrelation function of the degrees of freedom corresponding to the environment. Right? And if the path is delta correlated, it will be this B operator squared. But typically it is B, whatever B is T minus 4 minus B T. And there are some constants in there. So last time we were thinking of the external perturbation as the noisy electromagnetic field of random phase. And when we looked on this autocorrelation, we got some rates of transitions between from population to population. This statement is very genuine, and probably after having all components, all ideas together, we can consolidate them in like brief 15 minutes rigorous derivation of everything. But now we are going just to take the concepts. So the autocorrelation functions of the path operators are responsible for the rates of the transitions, and especially for transitions that change occupations of the levels. Good? On one hand. On another hand, we are going to believe, we are going to agree that whatever path we have, we will describe it as a collection of harmonic oscillators. Okay? Now we need to merge these two things together. So the operators for whom we need to find out the correlation functions will be some simple combinations of the operators describing harmonic oscillators of the path. Let me, although it looks simple, I better verbalize it and then we'll go further. Which are composed of harmonic oscillator creators and initiators. So what can serve as the path operator? let's talk about Hamiltonian without rigorous. If the path is electromagnetic field, then can be dipole by electric field, right? And Jabet was trying to show that amplitude of electric field can be composed as can be thought of as a coordinate of some oscillator. If you look into nuclear degrees of freedom, then we will have non-adiabatic coupling times momentum, right? So this will be system operator, this will be path operator. And momentum is the subtraction of creation and annihilation. But to most of the cases that we can think of that we need to model, the path operator will be linear in this harmonic oscillator creators and annihilators. So in order to process the rates, we will need, well, such linear combinations can be, brackets can be always opened, and then we will need autocorrelation functions of operators corresponding to harmonic oscillator at different instants of time. So as soon as we establish procedure, as soon as we establish a skill to evaluate such autocorrelation functions for both in the thermal equilibrium, we will be able to very quickly process and develop equation of motion for electronic degrees of freedom. So all rates, all constants in the equation of motion for electronic degrees of freedom will be composed of such terms. And as a benefit, we will automatically include the detailed balance principle. The flow of energy in and out will be automatically taken into account. So it will be getting success in achieving our goal in following dynamics of electronic degrees of freedom for open system that interacts with environment and can lose energy, can dissipate energy and go to ground state, towards the ground state. Make sense? More or less? Equation of motion for dissipation of energy. Dissipation of energy. So just in case we have forgotten what we are doing, it is a reminder. At least to myself, that I don't forget what to do. So this is the big goal, and this one is a technical one. Any ideas? How can we find what they are equal to? Any ideas? Can you look forward and develop some expectations? This should be simple. As soon as we agree on all conceptual ideas, the whole derivation that we do for that we discuss for 4 meetings can be done in 15 minutes. So it will be really quick and simple. And, this must be done under assumption that harmonic oscillators are in thermal state. So the oscillators themselves are described by density matrices or by statistical issues. So they are not quantum in a sense that they are not pure quantum. You cannot, for this thermal state, one cannot use wave function. You have 0 off-diagonal elements, but there will be population contributed by developing depending on the temperature. So there will be, for each oscillator, there will be distribution of populations corresponding to thermal equilibrium. Isn't that nice? So for each oscillator, there is distribution of populations according to thermal equilibrium. So there will be a little bit population at 0, a little bit of population at 1, a little bit population in 2. And we need to use this information in order to process these autocorrelation functions. Please try.
I have no idea.
You do. I have confirmation from the instructor who taught this course to you. It's just a couple of letters.
Is it the ratios between the populations?
Oh, we know that.
So then it would just be.
We know that it's all normalized. You can use different color. So this looks much better. Some normalization. Perfect, perfect. Good. You can see. So I will just take records after evaluation. So he already introduced partition function. The hardest part is behind. Now we have only simple math, which we can, well, I don't know, maybe you are well skilled, I can make an errors, but generally, conceptually, we have everything here.
what is E sub I? And is it plus or minus?
Oh, it should be negative.
That's not important. Who cares? Plus, minus. Some sign.
Both.
Yeah. Okay, so what is E sub I? It is simple. No doubts. 4 harmonic oscillator of given frequency. Just this. Okay. But even simpler. Forget about operators. I is a number of level. Well, now instead of n, it is I.
Yeah.
I plus 1/2. Perfect. Yeah. Many things. So, see, you know everything without any instructor. You can derive quantum theory of relaxation by your own.
I don't think so.
You do. So, now we need to merge together, for example, like this one, and this one. We are almost ready to do so. The only missing part is the partition function, which is not a concept that most of people remember in the middle of the night, like waking up, like, oh yeah, partition function. Probably not. But we know that some of the occupations should be normalized, should be equal 1. So if we add together,
Is this only for the vibronic position function?
yeah, only for neutral. Right? So, anyone wants to give a definition of partition function? Verbally.
Isn't it the integral of
Physical. This is mathematical. But like, what is
Total energy system? Some sort of sum of energies.
so some
ratio?
Sum of probabilities.
Some of all energy. Some of the energies evolve also from microstates.
something like this. So there is a physical meaning, and the higher the temperature, the larger number of microstates is accessible. So it should be temperature dependent, right? So at lower temperature you cannot access at low temperature you cannot access high energy microstate. So the higher the temperature, the larger number of microstates is accessible.
That's why the negative sign is important.
Yes.
Well, I was kidding. Negative sign is of course important.
It's the
The higher the temperature, the larger number of states is accessible. I don't think we need any of here. I'm going to make a screenshot and then we'll continue little exercises.
I already ate a donut.
You need to depart?
no.
Just gonna take a screenshot.
Oh! Okay.
But is that You're having way too much fun with old canvas.
I just need film to develop. That's all I
You know, in the past, the slides on presentations were not PowerPoint and were not even this projector letter size transparent slide. There were like little chops from the film, and they were projected. And typically, it was an operator who was projecting the next slide.
Or if they were really good, they had a little clicker.
Yep.
I doubt it works.
We're taking a picture of that.
Yes. I'm playing this for $50. It doesn't work right. Not on me.
So, do you recall from the top of the head the Q of T?
Q of T. Isn't it like 1 over 1 minus e to the something kt?
I think so, but I have fear to
That's-
forget.
that's-
We
that's
can
if-
try to
If you
rewrite it.
neglect the 0 point
Huh?
energy. That's if you neglect 0 point
Mhm.
energy because it's only relative energy that matters.
Let's just practice. So, according to Aaron, and everything which is the same for, well, if you want to be rigorous, we need to put 1/2, but we can assume that it will be part of the cube. Pull it out of brackets. So let's evaluate the sum. So if it is negative and temperature is big, then this is typically something less than 1. You can call it maybe x. Right? I know that Diane knows the answer because it is what he needs to do in his everyday research life to make summation of series. But let's go through little steps. These, let's call the approximation of zeroth order is when summation from 0 to 0. So it will be just 1. Approximation of first order will be 1 plus x. This is 1 plus x squared plus x cubed. Right? And 2 plus x plus x squared. And 3 1 plus x plus x squared plus x cubed. So we do have, we can look at it from two sides. From one side, from side of definition, we can tell that n of the I plus 1 equals n of I plus x to the power I, right? When you go to the next order. Going here, 1 plus x to power 1. Second, what we had before, plus x squared. Next, what we had before, plus x cubed.
Should you then need I plus 1 for x?
Correct. Thank you. Can we look at it from another aspect? Can we see, for example, here, you can identify Would it be correct? Yes? This will be right? So n of I plus 1 will be 1 plus x times n. How can you call it? Because writing equations can be not seen on the screen, and you need to communicate with colleagues. When previous term has some relation to previous one, previous and next.
Serious?
Huh? Series? Maybe recursive? Something. Relation. This one, this one, this, times. What can we do? Huh? Solve it as a system of equations. So if both are correct, we can state that left parts of first and second are equal. This one, this x times. What do we need to find?
X.
No. X is already defined. X is x equals e minus h bar divided by kt.
So then X is constant.
Yeah, well, parameter. So, well, you can constant for you. We need to find n for each number at I equals infinity. So let's just put everything related to n on one side and everything not related to n to another side. So n I 1 minus x equals 1 minus x equals 1. Make sense? No cheating? At least no cheating identified. You didn't catch me. And your q of t is limit of I going to infinity. If you assume that x is less than 1, then 1 minus very small parameter to the big power will be neglected. So, so 1 over 1 minus x. So if there were no errors, then this q function is 1 divided by 1 minus x. Exponential minus h by omega divided by kt. Similar to something that you saw before. How does it depend on temperature? So if temperature equals 0, finally divided by 0 will be infinity, exponential to the power minus infinity would be 0. So it should be 1. Right? Can we treat it as 1 microstate is available at 0 temperature?
Ground state.
Now let's Pt equals h bar omega. So temperature equivalent to frequency of vibrations. It will be not pretty radicals. It will be 1 divided by 1 minus T minus 1, which will be 1 divided by E minus 1 over E, which will be 1 over E minus 1 divided by E, which will be E divided by E minus 1. So like 2.7 divided by 2.7 minus 1. So about 1.5. Increasing. And if we put
Wouldn't it be 2 to the 7 squared?
huh?
Why is it
It's minus 1.
e divided by e to the minus 1?
E divided by E minus 1.
Oh, e minus 1, I see.
E minus 1, not power. E minus E as a number, minus
Right.
1 as a number.
I see.
2.7 minus 1.
Yeah.
And if the temperature is infinite, then exponential to the power 0 will be 1. Right? So 1 minus 1 will be 1 divided by 1 minus 1. 1 divided by 0 will be infinity. So at infinite temperature, there will be infinite number of microstates available. Make sense? Okay. We are doing good. We are happy with ourselves. But we didn't yet approach our goal. So in order to get relaxation rates of population, dissipation of energy or transition from occupied to unoccupied, we need to learn how to process autocorrelation functions of these operators and make them to average them over thermal equilibrium state. So probably I can erase anything except this little navigation. A little question. Just a refreshment of what we did a year ago.
Oh, I could do this one.
You do the next one.
Oh.
Which is easier.
Molecular communication relations.
Yes.
I think you're right.
Further please.
Oh, I guess I couldn't have done this one.
Ideally, we all should memorize it in the middle of the night. But if you do not recall, one can derive it.
Are we trying to,
further.
Oh.
are we trying to get some uncertainty here?
No, just commutation relations.
So you-
They do not quantum operators for harmonic oscillator do not compute. Well, not only for oscillator, they generally position and momentum.
This
do
one
not-
is general operator or?
General operator. What is commutator?
So
Zero
if
or
it's
non-zero?
coming. Oh, in this case,
Zero or non-zero?
it depends on the commutator. I don't know which commutator P and Q is.
Momentum and.
There is a very exact
Oh.
answer. And
So this one is momentum operator and Q
is position operator.
Oh, okay. It's minus.
Perfect question for any exam, even for thesis defense.
I
This
don't
is
know
something-
exactly. Yeah. So okay, I can come from X minus.
Does he have inequality?
It is something. This question has very specific answer, non-ambiguous.
I think.
Huh?
So it should be.
And the rest of you know the answer, or know how to get it.
So
No,
this
no,
will
no,
be
no, no, no.
just-
Before we go to further errors, this applies to x.
Yeah, then that's why I just write it.
And what is the derivative of
Yeah.
x over dx?
Yeah, it should be that.
Okay.
Then it's going to be height.
Perfect. Thank you so much. That's correct. You're ready to go for defense exam. At least in some aspects. Is it clear what Javid did? No questions, right? So he used the definition of momentum operator and assumed that they are working on acting on a wave function, and then just by the derivative of a product, he got another term that is responsible for commutation.
I know this.
Now me?
Yes, but you can like request help from a friend.
These things? Are they some?
You can put them, but still there is a very simple answer. It's not.
We did this in class, didn't we?
From minus
Huh?
minus
So,
one.
just follow the expert.
Minus one. Yeah.
Why? Thank you. That's correct.
Oh, perfect.
So why it is so? Yeah, we're not going to rewrite it, but it is correct. And how do we come to?
The first operator goes
Well,
to zero.
If we express the Q as function of A and A dagger, we should be just sum and some factor in front, and we express momentum. Yes, A dagger is also another constant, and we just use the original commutation. Then it will help us to generate the commutation relation for this A and A dagger. What is the meaning of A dagger A? Based on before we were using it in the
State.
it is number operator. So if you use definition of this operator and you agree that your quantum system is in state with number I, then you'll get I. Or here is the wave function. Here is the operator, and here is the number. So it is number operator. If you find expectation value of this operator, you will get the. If you use factor in front, it will be operator of energy. If you use it without the factor, then it will be average number of excitation, number of excited state. If it is a eigenstate, it will be discrete. If it is a superposition or mix, it can be non-integer between average number of quanta in a given oscillator. Average number of quanta in a given oscillator. So let's forget about these times and just do E dagger A with understanding that it corresponds to thermal state. Then we cannot use concept of wave functions. And we need to use the density operator that will depend on temperature. So it will have no off-diagonal elements. Everything will be diagonal with weights corresponding to this Boltzmann.
Why is the energy multiplied by the eigenvalue? I mean, the energy.
It's not energy, it's h bar omega times number of quanta. right? So we need the number of quanta multiplied by the weight factor, which is Boltzmann divided by this Q. So it is again a thing that I believe Diane knows how to do immediately, how to make summation of series. Any ideas? Actually, it is the step where I believe I made a mistake at home, but maybe together we will not make this mistake. What if you put this Q to the front? And let's make a very little numerical experiment. If you have an exponential product of two variables and we take a derivative over one variable.
So first times the second, this is second times the first. Chain move.
So
Yeah.
if we need to have the I up front, can we just take derivative over everything except I? And then, since derivative doesn't depend on the summation index, we can probably swap these two operations. No objections? And then, what will be this summation? How does it differ from what you had before? Not much. So it's just definition of this Q function. So the calculation of expected number of quanta in the harmonic oscillator that resides in third equilibrium is equivalent to derivative of the partition function over this strange argument. No error by now. At with no error identified. And here you can put just 1 over let's finish now. Double check that you do it correctly and start from the same point when we meet next time. But this function, as soon as we find it, will be the number of pointer in the mode when it is in a thermal equilibrium. And the result will correspond to Bose-Einstein distribution. So it will have a very similar shape to this one. As soon as we complete this procedure, we will get time dependence just by going forward and back from interaction to Schrödinger picture. It will be just oscillations, accumulation of phase. And these expectation values will be computed based on this statistical approach. So then we will carefully write down all components and mix them together into equation of motion for electronic degrees of freedom, which will have much more condensed form, so than amount of space that we spoiled during this exercise. Meeting number 23 is finished. If you have time and steam, you're welcome to visit the lab on Wednesday night, 3 p.m. And we will continue meeting number 24, same place, at noon on Thursday. I'll stay here a little longer if there are more questions. And I am putting us away from the record.
Oh, are they gonna be red-eyed?